It's a logistic.
Doesn't seem to work though. So I'm going to talk about the degree-corrected stochastic block model and its spectrum. This is joint work with Marc Lelars and Laurent Massoulier. We have also been working with community detection, which amounts to clustering and graphs. And instead of working directly with real networks, we start off with simplified models. So one of the most elementary such models is known as the stochastic block model. And it's a random graph on n vertices that are partitioned in two equal-sized communities. And then we construct our random graph by drawing an edge between any two vertices with probability a over n when the vertices belong to the same community, and with probability b over n when the vertices belong to different communities. And this is a nice model. It has been studied a lot. It's analytically very tractable, but it has as a drawback that vertices in the same community are stochastically indistinguishable. In particular, all vertices have the same expected degree, and this is not a very realistic setting. So instead, we worked with an extension which is known as the degree-corrected stochastic block model. So this is again a random graph on n vertices divided into two communities. But this time we had also IID weights to all the vertices. And then we construct again a random graph, but drawing an edge between any two vertices with a probability that depends again on the community membership of the vertices, but also on the weights of those vertices. And we studied this degree-corrected stochastic block model, we studied in its sparse regime. So this means that numbers a and b here are constants. So there are, this means in particular that the number of edges in the graph is of the same order as the number of vertices, so that there is very few information in the graph. And it actually turns out that traditional methods, such as using the adjacency matrix or the Laplacian matrix to study the graph, they break down in the sparse regime. They no longer work. So we have to find other methods to detect communities in this sparse regime. The method that we use is based on a matrix that's called the non-backtracking matrix. There's a matrix defined on the set of directed edges. And if I have a pair of directed edges, if the edges don't touch each other, I put the non-backtracking matrix to be 0. But otherwise, if I have a pair of oriented edges that are laying head-tail, then I put the non-backtracking matrix to be 1. Except when those two edges make a backtrack, then again the non-backtracking matrix is defined to be 0. So in 2013 there was this paper where people proposed an algorithm based on the second eigenvector of the non-backtracking matrix to do community detection in sparse graphs. And this they showed that this algorithm had actually a very good performance on real data. So to test this non-backtracking method in a principled way, people have investigated what it does on the ordinary stochastic block model, so the setting where there are no weights in the graph. In this setting, if A and B are very close to each other, then the communities resemble each other. So it's very hard to distinguish between the communities. And it actually turns out that if A and B are too close, then it's impossible to come up with a clustering that's better than random guess. And on the positive side, it turns out that the non-backtracking matrix is able to, that one can use an algorithm based on the non-backtracking matrix to find a positively correlated clustering when we are exactly above this threshold. So this says actually that for the ordinary stochastic block model, the non-backtracking matrix is optimal in the sense that it manages to find a clustering strictly better than random guess all the way down to this detectability threshold. So those results are known for the ordinary stochastic block model. We have extended those results to the degree-corrected setting. So this time the first question that we ask ourselves is, when is detection impossible? It turns out that there is again a very easy condition that depends this time also on the parameters A and B, but also on the second moment of the weight distribution. So if this condition holds, then again it's impossible to detect communities. It's impossible to do better than random gas. And now in this setting we ask ourselves, when is detection possible? Is it just possible above this threshold, or is something else happening in this model? And in particular, could we use the non-backtracking matrix to do community detection just above this threshold, or do we need to modify it? And do we also need to know any information about the weights, or can we find an algorithm that just has to look at the graphs to find communities? We answer those questions in the main result of our paper. I'm going to state it now informally. To do so, I need two constants, namely rho, which is equal to a plus b over 2 times the second moment of the weight distribution, and another constant, mu, which we put equal to a minus b over 2 times the second moment of the weight distribution. And I use this picture to explain our theorem. We always have that the leading eigenvalue of the non-backtracking matrix, so this one here, it's asymptotically equal to rho. So with asymptotic, I mean the setting where the network size tends to infinity. To say something about the second eigenvalue, we have to distinguish between two cases. When mu square is larger than rho, then our result says that the second eigenvector is asymptotically equal to mu. But otherwise, when mu square is smaller than rho, it turns out that the second eigenvalue is bounded by the square root of rho, so the square root of the leading eigenvalue. And we also obtain that the remaining eigenvalues are asymptotically bounded by the square root of rho. So we always have a leading eigenvalue, then a bulk of eigenvalues that are confined to a disk of square root rho, and we have a second eigenvalue that's either laying inside this disk or just outside this disk, clearly separated from the bulk of eigenvalues. And it turns out we showed it as a consequence when mu square is larger than rho, so when the second eigenvalue is clearly separated from the bulk of eigenvalues, that in this case we can use the non-backtracking matrix to find a clustering that's positively correlated with the true community structure. We also have a corollary to this main result. It's informally stated as follows. It's that the Greek-corrected Adams-Rényi graphs are quasi-Ramanujan. So this is the setting where, with the Greek-corrected Adams-Rényi graphs, I'm talking about a setting where A and B are both equal to 1. So when there are no communities in our graph. And then it follows that our leading eigenvalue is asymptotically equal to the square root of the weight distribution. But all the other eigenvalues are bounded by the square root of the second moment of the weight distribution. So a short conclusion. It was already known that the ordinary stochastic block model contains a phase transition, meaning that there is a threshold. Below this threshold, it's impossible to detect communities better than random gas. But just above this threshold, non-backtracking matrix was shown to come up with a positively correlated clustering that does do strictly better than random gas. And we extended those results to the degree-corrected stochastic block model. So again, there is a phase transition, a regime where it's not possible to do community detection, but just outside this regime, the non-backtracking matrix succeeds again in detecting communities. Meaning that for those two models, the non-backtracking algorithm seems to be optimal for community detection. And it's interesting to note that the non-backtracking matrix does not need to know any information about the weights in our graph.